All right, recording has started. I have a volunteer that like to write the answer for us. So this you just should have typed in. And I want you to enter the answer as if you were typing it into your OHS quiz or test. So if this was a quiz or a test question, it says round to the nearest thousandth. I want you to write down the answer as if you were typing it into the module there. Antonio, I volunteer you. All right, go ahead and write the answer for me. 0.700. And do you all agree with that answer? All right. Now, I chose this question because on Friday, all of you had your quiz for 3.0. Let me double check. 3.02. So your 3.02 quiz was Friday, and possibly, if because questions are kind of randomly drawn from the pool, you may have gotten a question like this, and your answer had trailing zeros. Well, in order to get credit for it, they wanted you to enter it, well, just like this. In this example, it's 0.700. I think after the that last zero goes like one something, like 0.7001. So right to the nearest thousandth, that's 3 decimal places. Just 0.700. Even though technically you could just put 0.7 or even just 0.7, but if you do that, it doesn't grade it properly. Don't ask me why. So you got to put this. So yeah, that is the correct answer. Also in quiz and test, especially your last test that most of you have already done, from question to question, it may switch how it wants you to round it. It may say round to the nearest 10th in one question, the 100th in another question, 1000th in another question. Even my part 2 of last unit's test, I asked you to round a very specific way on 2 different questions, and some of you just right over your head. So if you don't round properly, I can't give you points. Sorry. If you don't show work, I can't give you points. A little bit, yep. So I think your part 2, Emily. I think it was, when I went through it, it looks worse than it is just because I graded it really just harshly. They're just tiny mistakes, whether it's rounding or something else. Yeah, I put comments. So guys, if you look through the comments I put in your submissions, your part 2 submissions, even if you get 100%, still open up and look at it. I usually put a comment or 2 about your work or an answer or something. So please look at those. All right, let's keep going. Okay, yep, I can help you later whenever you'd like, after, obviously not during class though. All right, today is day 1 of 3.03, changes in amplitude and period. All right, we're being recorded. All right, GeoGebra, make sure you have your GeoGebra website, the graphing calculator, open. We'll be using that, and obviously paper and pen or pencil. Okay, this is just a quick refresher. These are the parent functions of the fundamental trig functions. We have the sine, cosine, and tangent. These are the other 3 trig functions, the parent functions: cosecant, secant, and cotangent. This is from last week. Okay, so today we'll be changing something called amplitude. So I feel like my slides are out of order. Let me go to this page first, and then I'll come back to this one. I think I have them out of order. All right, so amplitude. So the amplitude is the height of the function from the midline. Now that's important. So in a standard trig function without any type of changes to the amplitude or period or shifting, the midline is the x-axis here. And the amplitude is from the midline to the max value on the graph. So from this point to this point, this is the amplitude. Now the amplitude of a parent function, such as this right here, which is sine of x, the amplitude is always 1. So from the midline to this highest point, that distance is 1 unit. So that is the amplitude. All right, is that clear what the amplitude is now? All right, all right. All right, so I'm gonna show you on GeoGebra changing that value, which is the value of a. So the value, the coefficient in front of your trig function, that determines your amplitude. So we're gonna change this value from 1 to, well, a number greater than 1 and a number less than 1, but greater than 0, of course. So I'm gonna go back to this. I'm going to show you in GeoGebra. Okay, there we go. Antonio, hop on mic for me. Do you see the GeoGebra graph here?
Yes, I do.
All right, good. All right, so make sure all of you remember how to change your x-axis into radians. I'm going to quickly give you a refresher. We go to settings here. The cogwheel hits settings, go to the x-axis, and then you're going to change distance. You're going to select pi over 2. Now I like changing mine to pi over 4, so I just select pi, delete the 2, type in a 4, and hit enter, and then it updates. Then I can close this window. All right, so that changes the x-axis to radians, so it's easier to see. All right. I'm going to zoom in just enough here. So the amplitude, we can see, so the midline is the x-axis at pi over 2. I can see from this point to here is a distance of 1. That's the amplitude. I'm going to jump ahead of myself and talk about period real quick. So from the starting, well, in this case, starting point at x equals 0, the time, or in this case x, the distance it takes to do a full rotation is called the period. So it goes up, then down, and then it starts over. So the period of this parent function is 2 pi. Because then at 2 pi, it starts over. So the same pattern repeats. So again, the period is the duration until the function repeats. So up, down, and then starts over. All right, back to amplitude. So I'm going to change the a value. So the standard, it's just 1. Doesn't change anything. If I make a 2, we can easily see, well, the amplitude changes from a 1 to a 2. And same thing over here. From here to here, it was a 1, and now it's also a 2. So remember, it's the absolute value. We're talking about amplitude. From midline to a min or a max, the absolute value, that is your amplitude. So we went from a 1 to a 2. I can change this to a 3. Zoom out a little bit, and we can see it went from a 2 to a 3. So the period doesn't change. So up, down, then up, and then it starts to repeat again. So that distance from 0 to 2 pi, that doesn't change when we change the amplitude. If I change this 2 to a 0.5 or a 1/2, we can see that the period doesn't change from 0 to 2 pi. It's still one cycle. But the max height or the min height, that distance changes from a 1 from the parent function to a 1/2. So amplitude is really easy. Whatever coefficient that value is, well, that's your amplitude. Very simple. How do I go back? I'll figure it out. Did it. All right. So, any questions on amplitude so far? Yeah, it's pretty easy. Oh, one thing right here, if A is less than 0, all this does, so if you have like just a negative coefficient, all it does is take a guess. What do you think it does? Yep, it just flips. Well, not over the y-axis. Yep, I believe it flips over the x-axis. Let's see. If I change that value to a negative in front, I'm not going to share my screen. I want all of you to change it. Yeah, it just flips over the x-axis. That's all. Flips upside down. Yep. So the absolute value of A is greater than 1. It expands it, and if it's, well, between 0 and 1, then it compresses it. That's it. Okay. All right, so number 1. What happens when we have the amplitude becomes a 4 for this cotangent of theta? What happens? Does the amplitude increase or decrease? It increases, yep. Oops, not cotangent. Oh, I'm jumping ahead. Hold on. Scratch that thought. That should be filled in. All right, so something about tangent and cotangent. Let me go back and share my graph and show you something about it, because these are the exceptions. So tangent and cotangent, they don't have amplitudes. It's because they have asymptotes instead. So whenever you change the amplitude, the A value of tangent or cotangent, it's going to change the steepness. So let's make this a 10 in front. Now, if you notice, it's very steep now. The period of tangent and cotangent, again, from last week, do you recall what the period of tangent and cotangent are? It is pi, yep. So the period doesn't change now. So if the amplitude is greater than 1, it makes it more steep. If I change it from a 1 to, let's say, a fourth, it becomes less steep. And if I change that even smaller, like to a ninth, even less steep. So it changes the steepness. So let's look at cotangent. So let's change what cotangent looks like. If I change this to a 4, we will see the steepness change. So it becomes more steep, just like tangent. If I change it to 1/4, it's less steep. That's all it does. So that 4 causes it to become steeper. If it's like a fraction less than 1, like 1/9, it becomes less steep. All right, and then if you always forget these, you can always just type it into GeoGebra and you can actually see the change to remind you. So that's the difference between tangent and cotangent versus the others. It doesn't change the amplitude per se, it changes the steepness. All right, cosecant and secant. So these actually have amplitudes. So when I change the amplitude from 1 to a half, what happens? It compresses, yes. Well, now remember, steepness only applies to tangent and cotangent. So you can say it shrinks vertically, it compresses, or the amplitude decreases. They all mean the same thing. I think I just wrote exactly what happens. Amplitude decreases from 1 to a half. So again, it shrinks vertically, it compresses, amplitude decreases. On your quiz, on your test, it's going to be very specific on the wording. It might even be drag and drop or like a pull down. But all those mean the same thing. All right. So we have 6 secant theta. What happens to this graph? So we got expands. What else can we say it does? Getting taller, sure. It stretches vertically. That's another way we can say it. Yep, stretches. Or we can say exactly what happens is the amplitude changes from 1 to a 6. Let's go ahead and everyone type in 3 and 4. I'm going to bring up my graph as well. 1/2 cosecant and 6 secant. Let's go to cosecant of x looks like this. Here's the midline. Amplitude is 1. Antonio, what was the amplitude of this?
Half.
1/2. Okay, thank you. So I change that to half. You can see our amplitude decreases from 1 to a half. And then from here, it was from midline to 1 or -1. That decreased also to a half. In this case, -1/2. So again, amplitude is from the midline to a min or a max. All right. Number 4 was, I think, secant. So let's see what that one looks like. Secant of here, secant of x. And Antonio, what was that value?
It was 6.
6. Thank you.
You're welcome.
Zoom out a little bit. We can see that amplitude changed from 1 to a 6. I wish there was an easy. If I hit this, so I have a pause button. If I hit this, never mind, I don't have a pause button.
So doesn't it really get shorter instead of getting taller?
Well, in talking about like secant and cosecant, I guess technically yes, but it goes positive and negative to infinity. So is it really getting shorter if it goes to infinity?
No.
Yeah, it really doesn't. Even though, like on the graph, well, it goes, however less in this case. We went from 1 to a 6, so maybe on the graph it looks like it's getting, I guess, shorter. But if it goes on forever, it technically doesn't get any taller or shorter. It's the amplitude that changes. But good point. All right, I'm going to stop sharing. Going back and forth from sharing is a lot of clicks. Okay, are we good on amplitude, everyone? Yeah, that's the easy one. Let's go to the hard one now. Period. All right. Again, I think I have these out of order. Now we'll go here. All right. So let's look at y equals sine of x. All right. I mentioned period last week briefly. So period is the duration it takes to do a full rotation. So from 0 to 2 pi to do a complete rotation before it starts to repeat. All right, now let's see if I change the coefficient of the x variable inside the parentheses. So let's make this a let's make it a 2. See what happens. What happens to the period when the coefficient is greater than 1? What happens?
Pi.
Let's be more general. So I'm going to chat. I was able to tab back into chat. What happens when that k value is greater than 1? It's less long. What's other ways? It shrinks horizontally. Yep. So we can say it shrinks horizontally, or it compresses horizontally. Frequency. Yeah. It technically, yes, our frequency does increase, but I don't think we're going to talk about frequency in that way this unit. So save that thought, Galen. All right, so when your k value is greater than 1, the time it takes to do a full rotation, it decreased, right? So it shrank. Before it took a distance of 2 pi to do a full rotation. When k is greater than 1, it takes less time to do a full rotation. So let's make that 2 a 4 to see what happens. Ooh, it takes even less time to do a full rotation now, where it takes us only pi over 2. All right, let's see if we make, so that kind of, if k value is greater than 1, it takes less time. Making k value less than 1 should make it take longer to do a full rotation. And sure enough, it does. We went from 2 pi to 4 pi. So it takes 4 pi to do a full rotation when k is less than 1. All right, as a quick refresher, the period for sine, cosine, cosecant, and secant, the period is 2 pi. This is from last week. I went over this. Now, the period for tangent and cotangents, that is pi. So it only takes pi to do a full rotation for tangent and cotangent. This is important. You actually might have a test question on this. I might ask you, what's the period of one of these trig functions? Freebie points, right? Now, there is a formula. So the period is calculated by taking 2 pi and dividing by that coefficient k for sine, cosine, cosecant, and secant. For tangent and cotangent, because the period is pi, that formula is period equals pi over your coefficient k. So you want to write these down. So the formula for period is 2 pi over k or pi over k, depending on which trig function you are solving for. So let's look at some examples. Cosecant. Cosecant of x over 6. So the parent function of this is just going to be cosecant of x. So a period is just 2 pi for cosecant. What is the k value for number 5? What is the k value? One over 6. Yes. It is 1 over 6. Very good. So we know the k value is 1 over 6. So let's go ahead and plug that into the formula. So the period should be 2 pi divided by 1 over 6. And we do the math. So we can take 2 pi multiplied by the reciprocal. And then what is the period of number 5 now? $12 pi. Yep. It is 12 pi. So in words, what does that tell us? If the period is 12 pi, or sorry, if the period is 12 pi, what does that tell us? It expands. And let's be really specific here. So let's go back to the definition of period. So the definition of the period is on this page, if you missed it. The period is the time it takes before the graph starts to repeat. So more specifically, if the period is 12 pi, it takes 12 pi before your graph starts to repeat, simply put. Now let's type that in. Everyone on your GeoGebra, type in cosecant of x, and then type in cosecant of x divided by 6. And let's see if we can see if, in fact, that it takes 12 pi before it starts to repeat. 1, 2, 3, 4, 5. It takes me 6 clicks to share my browser. That's ridiculous. All right, cosecant of x is this. So there's the top one, there's the bottom one, and then there's 2 pi, and then it starts over. So it takes 2 pi before the graph starts to repeat. Okay, which is what we expected for the original. All right, let's type in cosecant of, what did I say, x over 6. And now, I gotta zoom way out. I'm gonna hide my other graph. All right, so there's the top one, there's the bottom one. And then we can see 12 pi's right there. So there's your asymptote at 12 pi. Then after 12 pi, your graph starts to repeat. So we got what we expected. The period is 12 pi. Pretty neat, right? So neat. All right, so number 6. What is the period of number 6? Pi over 4. Oops. So we plug the k value in, which is 8. And yep, we get pi over 4. So let's go ahead and type it into GeoGebra. I will do the same. All right, so cosine of x. What was the original again? I forget. Or sorry, yeah, what was it? Cosine of what? Cosine of 8x? Okay, thank you. See if that changes. And so we go from 2 pi to a pi over 4. Yep. So it goes down, then up again. Then at this point, we start to repeat, and that's at pi over 4. So yeah, we got what we expected, pi over 4. All right, everyone try number 7 and number 8. I'll give you 30 seconds. And these I won't show on the graph to save time. All right. What's the period for number 5? I mean, number 7. 2 pi over 3? Yep, I think that's right. The k value is 3. We just take 2 pi divided by 3, and that's already reduced. And if you were to type number 7 in your GeoGebra, you would see that it takes 2 pi over 3 before your graph starts to repeat. So that is correct. Number 8, what is the period? Got a bunch of 6 pi's. Anyone else agree with 6 pi? Yeah, you have to set it up. Was this a tricky question because it was cotangent and not another one? What is the period of cotangent? Pi. Yep. So to find the period of this number 8, you should have used period equals pi divided by k. Is that right? And then the k value in this problem is 1 over 6. Yeah. So let's see what that looks like set up. Okay. So I see a lot more 6 pi's in chat. Does everyone agree it's 6 pi now? And to confirm, just go ahead and type it in GeoGebra. It is 6 pi, yep. So cotangent. So the period is 6 pi. All right, any questions on these problems here? Nope, we're good. All right, so graphing these by hand. And whenever you graph these by hand, you always want to check in GeoGebra. It's a tool to use. I really hope nobody misses these problems when you graph them for your quiz or for your test. So knowing the parent function is definitely always helpful because it's really, we're moving around like min-max values and also your the period points. So we'll determine how the amplitude affects it and how the period affects it, and then we will apply those transformations. Let's look at 2 of them. All right, I went ahead and I just plotted the points. So for number 9, these points are for cosine. So y equals cosine of x. We start at 1, and it takes a distance of 2 pi to repeat. So I just plotted the same point from here to here. Halfway between. So at pi, that's going to be your, if these are the maxes, that means the min is right between them. And then that means that it crosses our midline halfway between those points. So at pi over 2 and at 3 pi over 2. So the standard cosine of x just kind of starts here, and we just connect the dots in a wavy motion. All right, so let's figure out the amplitude and the period. All right, what does this foretell us? The amplitude is 4. So that means that my new point, I'm going to use a different color. I'll use red. I think that's red. Oh, wait, no, I'll use this gold color. Or yellow. I'll use yellow. That's easier to see. So we're going to use, our amplitude changes from 1 to 4. Oh, I'm not using my pen tool. Let's try that again. All right. So it changed from 1 to 4. The period. Everyone calculate the new period. Then go ahead and tell me in chat what it is. Oh, that's green? Oh, I thought it was yellow. Okay, cool. It's green. And the new period is pi. So that means it starts to repeat at pi. So I should have that same point here. So it takes only pi to start repeating. So that means halfway between those points is going to be the minimum amplitude of 4. So I plot that point down here. Does that make sense of how I figured out that point? Yep. Yeah, graphing the original and seeing that motion, that's why I have it in blue, those blue points. All right, so the midline is between the min and the max. So that means it's going to cross here, and it's going to cross here. All right, and then once you have those points graphed, I'm going to go ahead and just connect them in a wavy motion the best I can. It's going to look terrible, I have a feeling. Not too terrible, I guess. And then everyone go ahead and graph that in GeoGebra and see if we get the same thing. And I guess I'll do the same thing. 4 cosine 2 pi, or sorry, 4 cosine 2x. Cosine 2x. All right, so there's cosine. Let's make that 4 cosine. There we go. Zoom out a little bit. All right, and we can see that first point the amplitude does change from 1 to 4. It repeats starting at pi. So we write about that. The minimum value is at pi over 2. We plotted that points. We plotted the midline points that were between this max and this min here. And we also plotted this midline point, and we just connected them in a wavy motion. So yeah, that is right. All right, everyone tried number 10. I'm going to give you all. You guys want like 2 minutes? That should be enough, more than enough, right? That should be more than enough to plot number 10 and also to verify in GeoGebra. 2 minutes. Now, if you notice, my graph on this page for number 10 is different than number 9. This one, I start at 0, of course, and then this one goes to 9 pi. So I'm doing 1 pi increments every tick mark, whereas this one was a pi over 4 for the increments. So keep that in mind when looking at this one. You can probably guess the reason why I chose this graph here is because it's going to get stretched out horizontally, right? So give you another minute. Then I'll take a volunteer to plot the new points for us and try to explain the best you can on your mic of what you're doing. All right, volunteer for number 10 to plot those points. All right, Emily, go ahead and plot it. Use green, please, and make your pen one or two, I guess, thicknesses higher, if that makes sense. And I would like you to explain and plot your midpoints first. Okay.
Okay, so on the calculator, you can see to calculate the period, you would do 2 pi. Oh, I can't type. 2 pi over 1 over 3, which ends up being, sorry, 1 sec, I can't type today, which ends up being 6 pi. So to complete a full rotation, so the midpoint would be between, right between 1 and 6. So hang on, let me get the pencil. I don't know how to do this. I am bad at Neuro. How do I change the size?
There is.
Oh, there. I see it. Okay. Yeah. I see it. I've never tried to change the size, so I had no idea how to do it. Okay, so it obviously starts at 0, 0, still. And then it would have a midpoint at 3 pi, and then also a point at 6 pi, because that's where it starts repeating. So then the amplitude, we can tell it's 2 because it's just the number in front. Whoa, that did not work. Wow, that's awful.
No, that's good. No,
in front of the sine function. So then you would go up from the midpoint to, and then down as well from, hang on, I'm so laggy today for some reason. I think it's because my computer updated. I'm super laggy.
So remember, I see you put this point here.
Holy crap.
These points
all of
that
a sudden I'm like freezing.
that's okay. These points here, these are your midpoints. So
sorry.
this is where it crosses the x-axis. So the max and the min couldn't be directly above those points. The height was right, but they go somewhere else.
I probably should stop because my computer is like freezing right now.
All right. Good job, Neuro. Mine does the same thing. All right, let me go ahead and finish what you started then, because this is a great start. Unless someone else wants to try to take over if their computer isn't freezing. All right, Antonio.
All right. I'm not sure how thick she made the pencil, so I'm just going to roll with this. It's going to be somewhere around here, I think. That was horrible. Hold up. Too thick. So I can't write, but just imagine that's better looking. In that there, and it's going to make the line going through it. You want to make the line?
You can. I think you're doing a great job.
All right, perfect. So say hello to Pablo Picasso, and there you go.
Good enough. Good enough. Yeah, something like that. And then we can go to our GeoGebra and verify this 2 sine x over 3. Let me Okay, so there's the original. I want to zoom out a little bit. So I think we said our period was 6 pi. So let me get 6 pi on the screen here. Oops. Okay. Okay, there we go. There's 6 pi right here. So here's 6 pi. There's 0. So that means our full rotation should take that distance to repeat. And let's see if it does. Oh, it sure does. So from 0 to 6 pi before it starts to repeat, we're right on that one. And the amplitude was, we said 2, which is here. So again, Emily plotted the midpoints at the origin at 6 pi. Halfway between those two is the other midpoint here. And then the min, the max would be between these two midpoints. So here and between these 2 points here and here. So that is right there. So yeah, relatively simple, I think. You know, again, always use GeoGebra to verify your answer. And these are piece of cake. All right, any questions on today's stuff? All right, so we only have 3 more lessons and we're done with this unit. It's like we just started. Well, everyone, well, thanks for coming, and well, I hope you learned something. See y'all tomorrow.